The C929 will become China's largest civilian aircraft to be produced since the Cold War. Wide-body passenger jet with a range of nearly 12,000 kilometers is designed by Chinese and Russian engineers.
For decades, the skies have been ruled by just two giants, Boeing and Airbus, locked in a quiet but fierce battle for dominance over the global aviation industry. But that era may be coming to an end. China's C929 has broken records with its impressive 12,000-kilometer test flight and sent shockwaves through Western aviation. Designed entirely with domestic technology and protected by independent intellectual property rights, the C929 marks a watershed moment in aviation history. It's not merely China's most ambitious aircraft to date, it is also a direct challenge to the status quo, signaling that a new contender has entered the arena with the power, precision, and confidence to take on the titans of the sky. Let's dive straight in. Origins and concept of the C929. The C929 is a massive technical and strategic evolution from its predecessor, the C919. While the C919 was China's first real attempt to break into the narrow-body market, dominated by the Boeing 737 and Airbus A320, the C929 aims even higher. Developed as a wide-body aircraft with a seating capacity of up to 280 passengers and an intercontinental range of approximately 12,000 kilometers, the C929 represents a quantum leap in technological complexity, material innovation, and global aspirations. The transition from the C919 to the C929 illustrates a methodical progression in China's civil aviation roadmap. While the C919 took flight in 2017 and entered commercial service with China Eastern Airlines in 2023, the C929 began its life as a joint international project. In 2015, China's COMAC, or the Commercial Aircraft Corporation of China, headquartered in Shanghai, partnered with Russia's United Aircraft Corporation, or UAC, to develop a next-generation wide-body aircraft under the name CR929. Backed by a projected initial investment of over $2 billion, the program was envisioned to tap into the combined strengths of both countries. China would contribute its expanding manufacturing and industrial capabilities. Russia would offer decades of aerospace experience. Under the agreement, COMAC was designated to lead development, manage final assembly lines, set to be located in Shanghai, and steer market integration, while Russia's UAC would support airframe design and advanced material applications, drawing from its expertise with aircraft like the Ilyushin IL-96 and Sukhoi Superjet 100. The aircraft was initially conceptualized with three main variants: CR929 500, 600, and 700, with the 600 variant being the baseline model, featuring a standard two-class configuration for 280 passengers and a 12,000 kilometers range.
A 280-seat wide-body passenger jet with a range of nearly 12,000 kilometers is designed by Chinese and Russian engineers.
However, the ambitious binational program began to encounter difficulties in the late 2010s. Technical disagreements emerged over the sharing and control of engine technology, avionics sourcing, and intellectual property rights. These tensions were aggravated by geopolitical upheavals, especially the outbreak of Russia's full-scale war in Ukraine in early 2021. With the conflict came sweeping Western sanctions, a reallocation of Russia's aerospace resources toward military production, and a sharp reduction in collaborative bandwidth. Russian engineers from UAC and affiliated design bureaus were reassigned to defense projects, causing severe delays on their end of the program. Simultaneously, COMAC had met its internal development milestones, creating a growing asymmetry within the project's timeline and vision. By 2022, the partnership had effectively collapsed. Russia formally stepped back from the joint venture, though certain subcontracted component suppliers remain involved at a limited capacity. China responded decisively by rebranding the aircraft as the C929 and recommitting to independent development under full domestic leadership. That decision bore fruit on February 20th, 2025, when COMAC publicly announced that the C929 had officially entered its flight testing phase. This milestone confirmed that the aircraft had passed key design validation processes, systems integration tests, and simulated certification requirements, bringing it one step closer to operational readiness. Equally important was the assertion that the C929 is protected under Chinese-owned intellectual property and is being developed to meet international airworthiness standards, an essential prerequisite for any aircraft seeking to compete globally, particularly in markets outside China. The development of the C929 is not only a technical achievement, but a strategic maneuver. It positions China to become a genuine competitor in the $100+ billion global wide-body aircraft market, which remains heavily concentrated between Boeing and Airbus. Should the C929 achieve certification and enter commercial service by the early 2030s, COMAC would possess the three critical pieces of a full civil aviation lineup: the ARJ-21, now rebranded as the C99, the C919, and the long-haul C929. This would not only diversify China's aviation industry, but also reduce its strategic dependency on Western manufacturers. Technical specifications and capabilities. With a projected range of 12,000 kilometers, the C929 clearly targets global routes such as Beijing to London or Shanghai to New York, positioning itself directly against established giants like the Boeing 787 Dreamliner and Airbus A350. In contrast, the C919, a narrow-body aircraft certified in 2022, has a range of only around 5,555 kilometers and seats roughly 158 passengers, placing it squarely in the short to medium-haul segment. The C929's configuration is built around a wide-body, twin-aisle design that accommodates three seating layouts: a typical two-class arrangement with 280 passengers, a high-density configuration reaching up to 310, and a premium layout with fewer than 260 seats for enhanced comfort. The aircraft features a fuselage diameter of 5.5 meters, slightly wider than the Boeing 787 and Airbus A350, allowing COMAC to implement broader seat widths and increased aisle space. With a wingspan exceeding 65 meters, the aircraft's aerodynamic profile has been fine-tuned to reduce drag and maximize lift during cruise. The C929 also incorporates 10 major aircraft systems, each designed to meet international safety and performance standards. These include advanced avionics, high-pressure hydraulic systems, electrical power systems, environmental control systems, fuel management, flight control, landing gear, onboard maintenance diagnostics, integrated modular avionics or IMA, and cutting-edge flight management systems or FMS. The avionics suite includes fly-by-wire controls and an integrated electronic flight instrument system or EFIS, consistent with 21st century aircraft standards. The high-efficiency wing design, featuring winglets and blended curvature, supports cruising speeds near Mach 0.85 while maintaining aerodynamic stability and fuel economy. Cabin comfort has been given a central role in the C929's development, with a focus on both noise reduction and pressurization systems. The cabin altitude is expected to be maintained at approximately 6,000 feet, on par with the Boeing 787, to enhance passenger comfort on long-haul flights. LED mood lighting, reduced cabin noise through vibration-damping materials, and improved air filtration and circulation systems are part of the standard design to ensure a modern flying experience. Material science plays a defining role in the performance and longevity of the C929. The airframe is composed of more than 50% carbon fiber reinforced polymer composites, contributing to a lighter structural weight, higher fuel efficiency, and greater resistance to corrosion. These composites are particularly prominent in the wings, tailplane, and fuselage skin. Titanium alloys make up about 15% of the aircraft's weight, used primarily in high-stress areas such as landing gear components, engine pylons, and critical joints, offering excellent strength-to-weight ratio and fatigue resistance. The rest of the airframe includes aluminum-lithium alloys and conventional aluminum alloys for cost-effective performance in non-critical areas. In terms of system integration, the C929 is a behemoth of engineering complexity, comprising approximately 2.2 million individual parts and over 3,500 specialized testing systems to verify functionality across all stages of development. It is also equipped with a real-time aircraft condition monitoring system designed to provide predictive maintenance data, reduce unscheduled repairs, and extend aircraft service life. The cockpit is built with smart systems, including touchscreen interfaces, synthetic vision systems, head-up displays, and advanced flight management features. Together, these systems will help pilots optimize fuel consumption, routing, and flight safety. But that's not all. The aviation technology supply chain backing the C929 is dominated by domestic Chinese companies, a strategic decision by COMAC to reduce dependence on Western aerospace firms. Out of 9 key avionics suppliers, 4 are Chinese, including major players like Avic Avionics Systems and China Electronics. Technology Avionics. The aircraft's central development and integration are managed by Shanghai Aircraft Design and Research Institute, a core subsidiary of COMAC, and the final assembly is based in Shanghai's Pudong district. This centralization of control allows for tighter quality assurance, coordinated logistics, and streamlined decision-making in the aircraft's iterative design process. The physical dimensions of the C929 also reflect a bold statement of China's competitive intent. With a wingspan slightly exceeding 65 meters, the aircraft rivals the 787 and is neck and neck with the A350-900. Its larger cabin cross-section and interior volume offer airlines flexibility to configure seating layouts for different market needs. The aircraft can work on anything from high-density tourism routes to luxury premium-class services on transcontinental flights. In terms of market positioning, COMAC has pursued a strategic cost reduction strategy aimed at undercutting Boeing and Airbus on price while maintaining comparable performance. By leveraging government subsidies, centralized production lines, and a vertically integrated supply chain, the C929 is expected to be priced significantly lower than its Western competitors. Early estimates suggest a unit price of $130 to $150 million, compared to $150 to $170 million discounted price for the Boeing 787-9 and $160 to $180 million discounted price for the Airbus A350-900. If COMAC can deliver on its promises of reduced operating costs and high dispatch reliability, the C929 could present a viable alternative in emerging markets and among national carriers in Asia, Africa, and parts of Latin America. With China aiming to capture at least 10% of the global wide-body aircraft market by 2040, the C929 is at the forefront of this geopolitical and industrial ambition. It is not just a plane. It is a statement of China's ability to break into a duopoly, assert technological maturity, and meet international demands with a domestically driven platform. But wait, the magic doesn't end here. Engine Autonomy, the CJ2000. Developed by the Aero Engine Corporation of China, or AECC, for the C929, the CJ2000 represents the country's most ambitious jet engine project to date. This marks a significant departure from the engine strategy of the earlier C919 narrowbody, which, despite being a Chinese aircraft, relied heavily on foreign propulsion, namely the LEAP-1C engine supplied jointly by CFM International, a GE Safran partnership. By contrast, the CJ2000 signals China's intent to sever dependence on Western engine makers and assume full lifecycle control of its large civil aircraft programs. The CJ2000 project, formally initiated in 2018 under AECC's Shanghai-based development division, was conceived in tandem with the wider C929 program. The engine is classified as a high bypass ratio turbofan, designed to generate 35 tons or approximately 77,000 pounds of thrust. In terms of physical dimensions, the CJ2000's fan diameter is projected at 3 meters. while its full engine height is estimated at 4.55 meters, dimensions that allow it to match the frontal surface area and airflow requirements of comparable Western counterparts. The CJ2000 features a twin-spool axial flow design with a large bypass ratio, possibly exceeding 10:1, an indicator of fuel efficiency and acoustic performance. The high bypass allows most of the air drawn into the fan to bypass the core of the engine, generating thrust more efficiently and quietly. This design is consistent with the latest international standards for fuel burn and emissions. AECC has incorporated advanced blade architecture into the CJ2000, using wide-chord fan blades made of titanium alloys with composite fan casings, reducing overall weight while maintaining structural integrity at high rotational speeds. Turbine blades are expected to be made from single crystal superalloys and feature thermal barrier coatings, allowing combustion temperatures over 1,600 degrees Celsius to ensure high thermal efficiency without compromising material durability. Noise reduction is another central goal of the CJ2000. It features chevron nozzles at both the bypass and core exhausts, along with low-noise variable pitch fan blades and high-efficiency acoustic liners inside the nacelle. Computational fluid dynamics modeling and digital twin simulations have been used extensively in the design process to optimize flow paths and reduce pressure losses. AECC is also emphasizing digital control architecture in the CJ2000's development. The engine will be managed by a full-authority digital engine control, or FADEC, system, developed domestically in coordination with the AVIC Group. The FADEC not only regulates engine parameters in real time, but also supports predictive diagnostics, adaptive control for optimal thrust in varying flight conditions, and efficient thrust management during cruise and climb phases. These features will contribute to improved dispatch reliability and fuel economy over the aircraft's operating life. AECC's testing facilities at the Shanghai Turbo Machinery Institute and the Turbine Engine Research Establishment in Shenyang are already involved in component-level tests, including high-pressure compressor and turbine stages. A prototype core engine completed its first test run in late 2023, validating key aspects of combustion efficiency and core stability. High-altitude engine testing is expected to take place at the Malan Air Base in Xinjiang, which has been upgraded to support civil aero engine programs. The CJ2000's success is integral to China's broader strategy of indigenous capability in civil aviation. Currently, the global market for large civil turbofan engines is dominated by General Electric, Rolls-Royce, and Safran, whose intellectual property and service networks create long-term revenue loops for aircraft engines sold abroad. For example, GE's engines often generate as much as 70% of their lifetime revenue not from initial sales, but from aftermarket servicing, parts, and maintenance agreements. A domestic Chinese engine like the CJ2000 would enable COMAC to not only avoid export controls and licensing barriers, but also retain domestic revenue from these secondary markets. Additionally, the development of the CJ2000 aligns with broader national policies, particularly the Made in China 2025 plan, which lists civil aerospace as a critical strategic sector. Beijing's 14th five-year plan further underscores the importance of aerospace self-reliance.
China recently issued a blueprint for the next 5 years, also known as the 14th five-year plan,
with specific targets to reduce reliance on imported core technologies, particularly in high-performance materials, microelectronics, and propulsion systems. The CJ2000 is central to these ambitions, and its successful deployment on the C929 would not only solidify China's position as an independent aircraft manufacturer, but also disrupt the current engine supply oligopoly. But it's not just about one plane or one engine. Broader vision, China's expanding aviation ecosystem. China's ambition to become a full-spectrum aerospace power has taken a significant leap in recent years with the strategic expansion of its civil aviation ecosystem. A key indicator of this maturation is the rebranding of the ARJ-21 regional jet as the C929. signaling its integration into a standardized aircraft naming system under COMAC, or Commercial Aircraft Corporation of China. Originally developed by Avic and entering commercial service in 2016 with Chengdu Airlines, the ARJ-21, now C929, features a capacity of 78 to 90 passengers and a range of 225 to 3,700 kilometers. It was China's first domestically developed jetliner to gain type certification from the Civil Aviation Administration of China and serves as the foundational step in a larger vision that now includes the narrow-body C919, the long-range wide-body C929, and a series of upcoming platforms aimed at redefining China's role in global aviation. The integration of the C929 into commercial service, expected in the early 2030s, would complete this lineup, providing China with an in-house solution across the full spectrum of civil air transport, from regional routes to intercontinental long hauls, while the C919, powered by Western-supplied LEAP-1C engines, entered commercial service with China Eastern Airlines in May 2023. The C929 is expected to seat between 250 and 280 passengers and offer a range of up to 12,000 kilometers. This positions it as a direct competitor to the Boeing 7879 and the Airbus A350-900, both of which dominate long-haul, wide-body markets. But the C929 is not the end goal. It is the bridge to even more ambitious platforms under development, notably the C939 and the concept stage C949. The former, now in preliminary R&D stages, is intended to rival the Boeing 777X and the Airbus A350-1000 in terms of size and performance. Targeting a seating capacity of over 350 passengers and a range potentially surpassing 14,000 kilometers, the C939 would cater to ultra-long-haul operations and offer greater cargo flexibility. Its development is expected to incorporate the lessons learned from the C919 and C929 programs, including airframe manufacturing, systems integration, and engine autonomy through the CJ2000 program. Even more radically, the C949 represents China's conceptual leap into next-generation aviation. Still in the drawing board phase, but publicly acknowledged by Avic and COMAC design bureaus, the C949 is envisioned as a supersonic, double-deck, triple-aisle aircraft capable of carrying over 500 passengers at speeds exceeding Mach 1.6. Slated for development by 2049, the centenary of the People's Republic of China, the C949 would not only dwarf the Airbus A380 in scale, but also incorporate high-speed flight technology, intelligent fuselage systems, and active aerodynamics. The triple-aisle configuration is being studied at research institutes like the Shanghai Aircraft Design and Research Institute, with potential applications of adaptive wing morphing, plasma flow control, and composite-intensive construction using over 60% advanced materials. These aircraft will depend heavily on sustained investment in experimental propulsion systems, hypersonic materials, and real-time digital flight control architectures, all currently being explored by Avic's Beijing Aeronautical Science and Technology Research Institute. The domestic economic case for such an ambitious lineup is strong. As the world's second-largest economy, China is forecasted to require more than 9,000 new aircraft over the next 20 years, according to COMAC and the Civil Aviation Administration of China. Of these, nearly 1,000 will be wide-body jets, aimed at supporting the rapid growth of China's international air travel market and the ambitions of its major carriers, such as China Southern, Air China, and China Eastern, to expand into global networks. With the US and EU often tightening technology exports amid geopolitical strains, there is a strategic imperative for China to decouple from foreign aircraft supply chains dominated by Boeing and Airbus. Each Airbus A350 or Boeing 787 purchased entails not just a massive cost, often in the range of $300 to $350 million per aircraft, but also long-term dependency on Western-made engines, avionics, and maintenance ecosystems. To that end, China's aviation supply chain is undergoing systematic reinforcement. AVIC and AECC are developing indigenous components ranging from flight control systems and avionics suites to high bypass turbofans like the CJ2000. The CAAC is also in ongoing dialogue with global regulators to push for recognition of Chinese certification standards, aiming to establish parity with FAA and EASA regulatory frameworks by the 2030s. Parallel initiatives, such as the integration of aerospace clusters in Shanghai, Xi'an, Chengdu, and Shenyang, supported by national policies like Made in China 2025, are further enabling industrial self-reliance. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.